Enjoy this discussion. Hi. So this is an example of my own creation. Alternate universe, Florida. So let's say we're in an alternate universe. Yes, ma'am. Don't worry, we're not suddenly transitioning to a multiverse physics, quantum mechanical kind of thing. Yeah. Yeah. Chapter 7 does not talk about alternate universes. I set this example up so we can explore the ideas of Chapter 7 in a more concrete way. I call it alternate universe Florida because what do you have down in Florida? Have you ever been to Florida? I'm sorry. I used to live there. Yeah. What do you got down in Florida? Who lives in Florida? Yeah. Some of them. Retirees, for the most part, yeah. And then just younger people, older people. So let's say the population age distribution looks like this. Alright, the shit's this mean? Here's 0. Yes, alligators. I remember reading the paper every morning. Some puppy got eaten by an alligator. You find gator skins out there. It was fantastic. And the water bugs that look like roaches that can carry small children away. It's an awesome place. Let's say it's 0 to 100. Let's just say, right? It's the weird Logan's Run thing where they kill you if you reach 100. So right here is 50. So does everybody get a feel? This is the age distribution in this alternate universe Florida. I have to say alternate universe Florida because in actual Florida there are people aged this, right? There are there's not no 50-year-olds in Florida right now. That would be kind of weird to claim. This is my alternate universe Florida, so too bad for you. So let's say, here's the mean is 50. And let's say the standard deviation is, let's just say, I don't know, Jeff. Doesn't matter. 10 or something. So now watch this. So if I go up 1 and down 1, I might not catch any data. Do you see that? All right. That's kind of like a separate discussion. How would this have been created? I know I just slapped it up here, but what would somebody have to do to actually make this distribution from scratch? Census. So what would a person have to do if they took it on themselves? They'd have to go to Florida and talk to people and say, how old are you? And say, I don't believe you. Let me see your driver's. Oh, I'm sorry. Keep going. You with me? So every dot here. Why is this really tall? Because there happened to be a lot of people that were this age, right? And then there was nobody in between these ages. Are you with, just randomly? That's just what happens. You guys understand the picture? This picture is nothing you have to do. I'm not going to give you a problem related to this picture at all, but we're going to investigate the ideas using this setup. Don't worry too much about alternate universe Florida. It's only going to show up right now for a minute. Okay, now, what if instead of doing that, asking a person, how old are you? I'm 3. How old are you? I'm 87. So walk around. Instead of doing that, I select groups of size 10, let's say. So let's make n equals 10. So this is n equals 1. This is one person at a time. Is this normal? Is this normally distributed? Oh, hell no. Normal would have the biggest peak in the middle. This ain't got shit in the middle, right? Just to show off my grammar. So instead of asking one person, how old are you, and then plotting it, I'm going to say, you 10 people. How old are all of you? Let me calculate your average, and then I'm going to plot that. You guys get what I'm doing? I'm going to create a different picture using the average age of 10 people at a time. Let me see if you guys can get this. What should the most likely average age be? 50. So that's the average. That's the real average. any group of 10, I'm going to expect the average to be 50. Because what's the most likely thing? Is this the most likely thing that I pick 10 people that are there? Just randomly? No, no. What's the most likely thing? I get a mixture from both groups, right? And their average would be around 50. What's the next most likely thing? I get a bunch of people around these peaks. You kind of with me? So if I graph this, obviously I didn't do this. Travel to an alternate universe. No. But here's what it should kind of look like if I do this. It should kind of look like this. A little peak here, and then a big peak. You make it right at 50. It's not going to be that beautiful though, Jeff. Oh, gee. And then a little peak. Okay, something like that. Looks kind of angry. Looks like it's giving us a thumbs up. Good job, Jeff. A middle finger shake. Depending on your perspective. So does the idea behind that make sense? Which one looks more normal? Neither one looks normal. Which one looks more normal? Second one. Now, what if I took a larger group? Now, see, this still could happen because 10, I wouldn't be surprised if we got 10 people here. But what if I took a group of 50? Then what really should almost always happen is a mixture of younger and older, almost always. It's going to be really difficult to be way down here, way up there, only in one chunk. I should almost always get mixtures. You guys see what I'm saying? If I randomly select 50 people, what's the probability I just randomly pick all these people right there? Very small chance. If you went out and randomly picked 10 people and they're all 98 years old, you're going to freak. You're like, where am I? What have I done? So if I do n equals 50, here's the neat thing that happens. You ready? Here's what happens. Here's 50. Becomes, in fact, to be honest, I'm going to bypass this number because it's not intuitive. But at 30, at a sample size of 30, the distribution, oh, you're going to love this shit, the distribution of sample means. Oh, come on now. Oh, shit. The distribution of sample means. What was this first picture? This was individual people's ages. And that ain't normal worth shit. I can't do anything to this to make it normal besides selectively kill people. Maybe I can kill all these people and then kind of smooth this out. And that's a little evil, right? Let's not do that. It's alternate universe, though, with the shit. We can have fun. So just take the insurance out on it. At 30, it becomes normal enough. And what's the average always going to be for all these pictures? It's always going to be 50. Does that make sense? If I took the average age in here, 1 by 1, I'd get a certain number. If I took 2 of you average, 2 of you average, 2 of you average, and then averaged all of those, it's going to be the same stupid number, isn't it? Do you guys get that? If I average each individual age, I get a number. If I took 2 of you at a time and averaged your ages and then averaged all of those, it's still going to be the same number. Why would it be a different number? You're still the same people. So every time I do this, the mean is staying the same. Now here's the little thing that changes about it. The symbol for it changes. I don't know if you guys have noticed, when you do 1 var stats in your calculator, I don't think it does. On the S and the sigma, it has a little X. Have you guys noticed that? So here's one reason why. When I start doing the mean of, this is the mean of what? Let me see if you guys can get this. On this picture, what's that the mean of? The sample means, right? This is the mean of all the sample means of size 10. So I'm not going to just use mu, I'm going to say the mean of all the sample means, mu sub x bar. So subscripts are normally descriptive of the thing. So that's the mean of the sample means. That's not mu divided by x. That's mu sub x bar. It just means the mean of the sample means. Say again? Yeah, I'll put it over here. So this doesn't say so, that's funny. Mean of the sample means. Do you guys remember this formula? Here. Say yes. What is that the formula for? Slope. I love it. What does little 2 mean? It's the y of the second point, right? And it's the y piece of the first point. It's the x piece of the second point. The y of the second point. The mean of all the sample means. Subscripts always mean more specific description. Go ahead. Now, we talked about the means. It stays the same. The mean doesn't give a shit if you take groups. It's going to be the same mean because it's still the same people you're talking about. Why would the mean change? But what definitely changes? What's the other thing that we always want to calculate? Standard deviation. So you get a standard deviation is 10. In which picture is the standard deviation bigger, the top or the bottom? Where's it bigger? The top, yes. Because doesn't the data get further away from the middle on the top picture? And then what happens from here to here? Even smaller still. You guys see that? Why does that make sense? If you walked outside and saw somebody who was 7 foot tall, you'd go, well, 7 foot tall, right? If you walk outside, you see 20 people who are all at least 7 foot tall. Will you react the same way or a little differently? You go, what's going on over that way? Are you guys with me? So it makes sense that the standard deviation is going to get smaller and smaller because there should be less and less stuff out here. There should be less and less stuff out there. If I took a group of 50 people, what's the probability their average age is 100? Very small, right? There's not going to be very many things out there. Most of them are going to be close to the mean, and what measures how close you are to the mean? Standard deviation. So here the standard deviation is smaller. This one, the standard deviation is smaller than the original. Look at that, standard deviation of the means. Do you see that? A little subscript. I love you guys. And then here, standard deviation of the means here is even smaller. Become a sigma. Less than sigma. Even smaller. So here's the formula for what the standard deviation does. The mean stays the same. So let's see. Let me write down what we've got so far. N greater than 30, sample mean, distribution, normal enough. Why is that important, that normal enough? Normal enough to do what? To not be laughed at. No. Normal enough to do what? What has to be normal before I can use it? That's such a weird phrase taken out of this class. What has to be normal? The distribution has to be normal before I can use what? Z-score chart. I like it. So if I know it's normal enough, I'm allowed to get the answers off that chart. All the answers are just sitting there waiting for me. But I have to know that the distribution is normal enough. So if I didn't take groups any bigger than 1, this thing is dead. 10, still no good. But at 30, every distribution becomes normal enough. Past 30. And they just get more, more and more normal the larger the sample you take. Now listen. I really want to make this point right now. If I took one sample of 30 people from here, that will not necessarily be normally distributed. That is not what I have said. If I took 30 people from here, it could be, these 30 people here and these 30. When I draw it, it doesn't have to be normal. There's no reason it has to be normal. What's normal when I hit a sample size of 30 is the graph of all the samples of size 30, their averages. That's what becomes normal enough. I know. So I could take one sample of 30, and it's not normal. But it lives, let me change this to 30 just so I can use this picture. No, that stays 50, Jeff. That one sample of 30 I picked might be that one right there. Right? And what was this picture? I take one person. Where are they? There, maybe. That's the guy I just picked. That guy right there. Right? So this is a picture of individuals. This is a picture of groups. Maybe. Now watch. So keep going with me. Keep going. Keep going. So the problems we've done before today, you had no problem. So if I said normal, mean is 5, standard deviation is 1, you would draw this picture, right? Right? And some of you guys are going to be like, but you told me to, man. Don't be trying to put... No. We drew this picture. You agree with me that that was a good picture to draw. It's normal. So what the shit does all this mean? Then I pick... What do? Pick one person. So one person, and I asked what's the probability that they're greater than 6? So what I'm asking is, that one person, what's the probability that they were up here? That they were somebody that I plotted up there. So now what's going to happen is, if I pick 30 people, I'm going to ask you what's the probability that their average is greater than 6. Then when you draw the picture and the numbers I use, it's going to be related not to individuals, it's going to be related to groups of 30. So in this one, what would change? The standard deviation would have to get smaller, right? Because this one, what's this one about? Individuals. What's this one about? Groups of size 30. They should be closer to the real average, every group of size 30. It should be much less likely for them to be really far from the average. If I took a random group of 50 people and their average age was 2, that's really good evidence I didn't randomly pick. I am in a nursery or something. Something is weird, right? So, here. The mean stays the same, but the standard deviation becomes exactly this much smaller. Hopefully it makes sense. The bigger my sample that I take, the closer everything will get to the mean. Yes?
So in order for it to be normal, it always have to be normal.
Either I got to say it's normal, and then it doesn't matter if I just pick one person, right? Remember, we've done problems like this already, where I picked one person. If I already know it's normal, I don't care what the sample size is. But if I don't know it's normal, I got to have a sample greater than 30 to then know it's normal enough. Yeah. I like it. Yes. As n gets bigger, as my sample gets bigger. So watch. If I took a sample of 10 people in here, would you say their average should be decently close to the actual average of everybody? Yeah, maybe. But if I took a sample of 40 people out of this classroom, and their average age wasn't really close to the actual average, wouldn't that be weird? So the bigger the group I take, the closer to the average they should be. What does that mean about the standard deviation? It should get smaller and smaller. So as n gets bigger, the standard deviation gets smaller. Okay. So let's try a problem out. Because if I'm you, well, let's do two things. Let me give you this remarkably colorful handout that you're going to enjoy so much. Look at the colorful side for right now, right? Don't worry about the other side yet. I know right now, go with me for a minute. Right now you're all like, what the shit are these problems going to look like? Is anybody thinking that right now? Yes? Stay with me for a minute. Hold on. This is still not what a problem's going to look like. This is still explaining the concept. Oh, I lost track. Who knows? See how many that's. Oh, there's one more extra. Let me take one. Oh, that's mine. That's we're bumping into people. This is admittedly a strange handout. I don't care, because this is a rather weird idea. Can somebody turn the lights down? So before we do an actual nuts and bolts, we're going for today, I like it. Nuts and bolts problem. I'll investigate the idea a little more. None of the calories, but all of the chemicals. Yeah. Sorry. There we go. All right. Everybody cool with the beginning of this? Put 4 numbers in a hat. It's a very kind of expansive way to represent that. Like 1 is represented by that bar. You guys cool with that? And of course they would all be have a height of 1/4 because there's 4 slips of paper. So they each have a probability of 1/4. So it's basically a uniform distribution, right? I didn't put more 1s in or more 2s in. Everybody cool with that? So over there I showed a probability distribution. Ooh. Does this look normal? No. But it does look much better than my alternate universe did, right? It's at least symmetric for sure. So it starts off kind of nice. So it should approach normal quicker. You shouldn't have to wait till 30. So look, even after just now, I want this. I love this sheet, and most students hate it. But oh well, you don't have to do a problem like this. But here's the concrete thing what I'm talking about. If I pick 2 slips of paper with replacement, I have to do it with replacement so all the probabilities stay the same. What could I pick? I could pick 1 and then pick 1 again. So what I've done is I've listed all of the samples of size 2. Sort of like if I went to Florida, I'd have to first figure out all the samples of size 30 and then actually take them. Oh shit. So there's all the samples of size 2. Is everybody with me? So my picture is not going to be based on the numbers on the paper anymore. It's going to be based on the averages of the numbers I picked. So that's in yellow is the new data. Does everybody see that? Oh, you guys, you're so excited. I know, I'm sorry. We can do this. So if I pick the numbers 1, 2, the average is 1.5. What's the most likely average? What's the most common average? What yellow piece number shows up most? 2.5, which of course was the average of the original, right? Okay. So if I take these and plot these instead, so 1 should be kind of a low bar, and then this should be a little higher, this should be a little higher, and then 2.5 is the highest bar. Does that look more normal already? Oh, hell yes. And again, it's because it started off nice. If it started off disgusting, I would have taken like n equals 10, but then that would have taken forever to list. Oh my god. N equals 2 was a pretty big chart. You can't, n equal 3 would be 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 2, 1, 1. Holy shit. Alright, so I've taken this group of 2. It already looks more normal. The standard deviation up here, look. So how did I calculate the standard deviation? I just, did x, b of x and all that shit, but I didn't show it to you. Are you guys cool with that? So there's what the standard deviation was from the beginning. Supposedly, now how big of a sample did I take? Size 2, right? N equals 2. So if I take 1.118 divided by the square root of 2, I should get the standard deviation of this. And sure enough, if you calculate the standard deviation, you do get the original divided by the square root of 2. And if you don't believe me, you can check me on that. Right? So most of you guys will be like, dude, I don't even know what you're saying. To start to think if I believe in what you're saying. I'm hoping you guys... So if I would have taken a sample of 3 and I listed all the samples, that would have been big, but I could have done it. And then I could have just calculated the standard deviation. What would it have come out to be? 1.118 divided by the square root of 3. Whatever the shit that is. it would have been much higher peak in the middle, much smaller on the outsides. If I take 3 at a time, there should be more on the average. So the standard deviation would get even smaller a little bit. Okay, all right. I'm gonna just accept that reaction. So, can you bring the lights back up? Let's do a nuts and bolts problem. This was still just the idea of it. What is this gonna do to you? I understand that is of utmost concern. So we do one of my favorite problems. I don't even know how to spell kindergarten. Kindergartners have an average height, let's say, of, just to make it easy, 40 inches. Does that sound about right? 3 foot, yeah, something like that. Yeah, sure. We'll go with that. This is heavily researched. Average height of 40 inches with a standard deviation of, let's say, 2.1. Just to make something to work with. Now, for right now, I'm going to tell you, let's say that they're normal. Heights are always normally distributed. So how big of a sample do I have to take to make it to end up with a normal distribution? I can take whatever size I want to, because it's already normal. So I don't need n greater than 30. Why? It's already normal. So if it doesn't say it's normal, what's going to save that problem's ass is if the sample size is bigger than 30. Then I can do something. If it says it's normal, who gives a shit how big of a sample I take? We already said it's normal. Do you guys get that? That's where that n greater than 30 comes in. Because if you have no idea what it is to begin with, they better take a sample bigger than 30 to save that problem's ass. What's the probability? So if I pick one kindergartner, what's the probability that they are shorter than 39 inches? All right, this is our classic old. We did this a long time ago, yesterday. So, what goes in the middle? Who?
Oh, sorry.
40? Yeah, we're not in alternate US Florida anymore, babies. And then 39 is here, and I want less than that, so this is going to be nice. I don't have to do any adjustment, right? What do I do next? Don't worry, this is nothing new yet. This is old, and then I'm going to do a part B. That's the new thing, okay? Z-score. Yeah, they're 40. Negative 0.48? Can somebody look that up for me real quick? Are you guys with us on that?
0.3156.
No, I got that.
You got that? And then 0.3156 from the Z-score chart? You guys getting that? Okay. All right, so that's old news. That's old news. To make it new, what am I going to have to do? 2 things. I'm going to have to take a sample and then ask a question about that sample's mean. You see the 2 things that have to happen? That's the key. What's the only thing from all that alternate universe, Florida shit, numbers in a hat, colors going crazy, weird ass shit? What's the only thing that changes as far as we're concerned? We got to change the standard deviation. That's it. So before you do a Z-score, if I take a sample of size blank, and then ask a question about the probability that the sample mean is bigger or smaller than something, you change the standard deviation before you make a Z-score. That's it. That's the only thing that changes. A lot of concept behind a very small change in the problem. So if I ask what seems to be the same question, so part number 2 would say, pick 38 kindergartners randomly. What's the probability that their average height is less than 39? So what's the very, very first thing I should do? Did it get triggered that I should change the standard deviation? They get it triggered. Did I do 2 things? Yes, I took a sample. Ask it about the sample mean. So we got to start to realize the thing I told you on day one. What was it about this problem that gets people down? This class, there are several things: the Greek letters, formulas, and then how each one changes. The concepts. This is a very concept-heavy class. So when do I change the standard deviation? When those two things happen. So what's the standard deviation become now? What it was, where'd it go? There. Divided by the square root of?
40.
Nope.
38.
38, there it is. N, square root of n, right? Whatever the size sample it was I took. The bigger the sample, the closer everything should get to the actual average.
So it's the size sample of that specific problem about the original information I gave you?
I didn't give you any sample information to begin with.
Oh, sorry, that
40 was inches height, yeah.
Got it.
Yeah. So now I can draw the picture. What goes in the middle? Yeah, it's still 40. The mean doesn't change. You could make it skinnier if you want to, but who gives a shit? Officially, it would be skinnier than this one was, but, you know. And I still have my 39 here, right? And I still want this area here, but now, can you guys see how the z-score is going to become much larger? Because it's going to be dividing by smaller. So, what? So this picture, what does this picture represent? Groups. Groups of size 38, they're averages, right? So I'm going to say this so many times, but I don't care. That standard deviation is good for individuals. When I take a group of 38, I can't use that one anymore because it's good for individuals. It tells me the spread for individual heights. I need the spread for groups of size 38. That's the idea, right? That's why we adjust this. I'm not making this into a sample standard deviation. It's still a population, isn't it? The population of all size 38 samples. So, anybody help me on this? What's this? 3, 4, 07. So let's say 1. I like it. You're good. You can use 3, 4, 7. You're fine. Yeah. I said at least 3 places, so you could use 4 places if you want to. Like, remember I said that, I think, on day 1. Just round everything to 4 places, except for z-scores. So now, look. So that is the one. Why is this problem taking long? I've talked a lot about it, right? This problem, basically the same. That says one more step. What was it? Change the standard deviation. What do I do now? Make a z-score. What's that formula going to look like now? It's like 3 almost, or 2.92. I don't know. Negative.
Negative 2.93.
It's my one skill. Come on. No. 2.9. What was it? 3? I love you guys are all like, still second. What?
It's 4 rounded.
2.94?
Yeah, this is a 5 out there.
Ooh, dissension. Yeah. What's up?
Oh, I went in 4 decimal places though.
Oh, I see.
Isn't it, it would be 38 or it stays at 39? The second decimal. Because we're 39 is X, right?
What's happening? Sorry?
C square, just right there, yeah. You said, yeah, no, 39 minus 40. Wouldn't it be 38 minus 40?
Of course not. Of course not. What's the question about? That's n. That's the sample size. Yeah, the question is about this data point. So I still got to change that data point to a z-score. So yeah, it depends. If you round it, if you use 4 places, you actually do come out to 4 at the end there, yeah. So either way, I depending on how much you round your standard deviation, I can accept different answers there. Yes?
And then, I missed the second thing. We change the standard deviation when we take a sample, and what's the other one?
Take a sample and ask a question about the sample mean. Yeah. Those are the two things that happen. You go, oh, I got to change the standard deviation before I can get z-scores. Oh man, I really oppressed you guys today. You're all like, ugh. Too bad. Here comes some more. So what? When you look that up, what do you get? Those of you that got the negative 293, what is it? 0017?
Oh, wait, yeah, I looked up.
0018?
That's right.
And if you got 2.94, what'd you get?
No, that, it was 7. Yeah, wait, no, it is 7.
Oh man, where's my z-score chart? Do I have any left?
Sorry.
Oh. 2.93. Yeah, 0.0017. And then for 4, it's 0016, right? Yeah.
So you take either.
Yeah. It just depends on how much you rounded your standard deviation. Yeah. All right, I like it. All right, so on the other side of that colorful, crazy ass thing are some problems related to rent prices in Waikato, New Zealand, and here at home. So go for it. Do this.